Hi everyone, thank you for joining us for this conversation dedicated to the different ways of achieving performance in the motorsports industry using additive manufacturing. For those who do not know me, my name is Katie Cindy and I am the managing editor at 3D Adept Media. There are so many people who register for this panel, so I would like to advise you to write any questions you may have in the Q&A chat from the very beginning, and we'll pause at some point of the conversation to discuss them. Before we move forward, I would like to give the floor to the presenters, yes, so that they can introduce themselves as well as the company they are working for. So Erica, can you go first?
Sure. Thank you, Ketty. Hi, everyone. My name is Erica Berg. I am the managing director of our business development and application engineering teams at Carbon. So we help customers understand how to use the technology to scale and best design for DLS. Carbon is a tech company based out of Silicon Valley. We make hardware, materials, and software for additive manufacturing. And I'm very excited and grateful to be here today to talk about motorsports and additive manufacturing.
Thank you, Erica. What about you, Andrew? Who are you?
Great. Yeah, thank you for having me. Hello to everybody out there. So I'm a product application engineer in additive manufacturing at General Motors. I work primarily on motorsports applications. So helped create a group there dedicated to serving our different motorsports partners as well as our internal motorsports activities. And I'm actually taking a little bit of time off an advanced manufacturing and design degree, but still staying quite plugged in with the racing activities that we're doing. Have a background before this in motorsports aerodynamics, wind tunnel models, and Formula SAE.
Thank you, Andrew. So motorsports is a high-tech industry which encompasses the organization of competitive race events of motorized vehicles like custom cars, motorcycles. In a nutshell, anything that runs on a propulsion medium and catches the fancy of racers and fans alike. No matter what type of competitive race events we are dealing with, this field requires ultra high precision in all the employee design and operations. And as we all know, additive manufacturing is a legitimate tool that can enable the level of performance and precision this field demands. However, if we are here today, that's only because things are not always that simple with AM. And the first things that we have noticed is that the motorsports industry is one of the first vertical that has adopted AM in the sports industry in general. And my first question to you, Erica and Andrew, is that if you had to mention three key items that show how the adoption of AM has evolved in this industry, what would you say?
Yeah, I would say additive manufacturing has made so much progress, especially in the recent years in terms of speed, quality, and scale. Today, you're seeing additive manufacturing used across the metal space or even polymers at really unprecedented scale that has never before been seen. And the ability to get to that scale is because we are seeing the throughput that's necessary and the ability to print parts at the quality necessary in order to break beyond a prototyping or niche support of manufacturing industry into scaled manufacturing. So from our perspective at Carbon, we are making parts that are going on cars. We're making components that are brackets. We've worked with major automotive companies globally. And we're also looking at various components that can go within the vehicle. And that's because of the ability to, hit the speed and the scale and the quality that's necessary in order to meet all of the approvals and validation. And of course, make it a compelling business case and reason for companies to use the technology to pull into their vehicles from a mass manufacturing perspective. So those would be the three areas that I would say we've seen significant progress, and I'm excited to see how we continue to evolve in the coming future as well.
Okay, interesting. So, Andrew, do you have 3 other items to mention?
Sure. Yeah, certainly echo everything that Erica said. Can relate to that all from the General Motors perspective in terms of the mass adoption really significantly increasing at an exponential rate. In motorsports as well, that's been the case. So if you look at, say, the Corvette C7R, we had less than a dozen additive components on the production race car. If you look at the current Corvette C8R, we actually have over 85 parts on that vehicle. And that sort of trend isn't unique. It's been continuing through a lot of our different motorsports programs, as well as it's starting to propagate into our mainstream production programs. You know, I see that as well. Looking at benchmark examples out in the public, when I first started doing this in 2018, it was very hard to find a lot of examples of additive and motorsports online. And now I have, you know, like a whole newsletter that I publish internally, where it's so easy to find all these implementations and adaptations of the technology. So yeah, certainly the widespread use in motorsports growing exponentially. The material capability has been huge in that. So having materials that can perform under, you know, high stress, high temperature, that are able to be printed highly consistently with, you know, great surface finish. So the materials is another big thing. And then I think culturally as well, because people are starting to realize, hey, this isn't just for prototyping. This isn't something that is going to break if you look at it wrong, right? These are just as functional or even more functional than other conventional techniques.
Yeah, thanks, Andrew. Erica, would you say that the challenges faced in automotive additive manufacturing are also the same that professionals that use AM for motorsports application face?
Yeah, well, I'm interested to hear Andrew's perspective on this too, but I would say from what I've seen, the two industries are targeting different end users and audiences. So from an automotive perspective, right, you're thinking of your average consumer who's looking to get a vehicle, and so the considerations of how to design for that end user is different than someone who is a professional and really looking to have the most elite performance in every single component of their race car or what they're driving. So, you know, from my team's perspective, when we're engaging with customers, that's how we start. We really want to understand our customers' goals and objectives and their end customers or their end users, so that we can know what are the true requirements that we want to design and drive to. And how do we meet those requirements within various constraints? You could have multiple constraints that might be the same between automotive or motorsports. And you're, of course, going to have different constraints or requirements that are unique to each of those industries. So that's been, you know, at a really high level, my perspective. At the end of the day, those two industries are focused on serving two different purposes. And in our interactions with customers, I really enjoy understanding what they want to really drive to and support in order to make a successful product.
Okay, so two different purposes. Andrew, do you share this feeling of Erica? I mean, do you share the same thoughts?
In some things, very much so. In other ways, there are a lot of similarities. So one of the benefits of having a motorsports application engineer, application engineers within the mainstream additive group is that extra spend for that last bit of performance, that new technology, the lightweighting, whatever it may be, can be spent in motorsports and can be proven out. And one of the things that we're seeing in additive manufacturing is the cost is dropping, you know, exponentially. The ability to produce parts is increasing significantly with the new machine technology that's coming online. So some of the things that are only possible in motorsports now in a very short period of time will be possible in mainstream production. So it's important to get ahead of those currently and understand, you know, all the difficulties, work out all the kinks before it needs to just be executed in a mainstream production program where they don't have time to do, you know, a multi-month or multi-year R&D type activity. And then there are, I think, quite a lot of similarities. One of the things that GM is working towards is being able to more quickly release vehicles out into the market. That's one of the industry trends as a whole, but it's something that we really see as a competitive advantage if we want to, update models regularly to meet new consumer demands as technology really increases rapidly, or if we want to be able to have broader customization, that ability to iterate and to change and to have customized parts. Or smaller scale runs of things that are beneficial in motorsports are also beneficial for mainstream production vehicles.
Yeah. Oh, Andrew, I would like you to take a little bit some experience, the experience of General Motors in this specific field, and tell me, usually any conversation that focuses on motorsports involves speed and performance. Do you think, engineers only look to enhance performance in motorsports applications?
Yeah, so performance is definitely key. My number one objective is to win. And I think that's going to be the case if you talk to any motorsports engineer.
Yeah.
At the end of the day, the stopwatch tells you if you've done a good job with your job. And so that's certainly at the very top. But everything needs to be justified.
Yeah.
There's not unlimited spending. Even in Formula One now, there's not unlimited spending. And so if there's a, say a set budget for a program, if cost, that money can then be diverted somewhere else. It's certainly not going to be, diverted back from the source. It will be spent in motorsports, but it will add performance in other areas. So maybe not directly adding performance by being cost conscious, but certainly something that can add it in the long run. And then the ability to, to iterate quicker increases performance too. So there are a number of, you can increase the performance from the part design itself, saving weight, adding stiffness, adding complex geometry for aerodynamic purposes, and then you can also add performance sort of on the back end by freeing up those dollars or freeing up that engineering or that manufacturing time to make the next iteration or the next system better.
Yeah. Yeah. Erica, I know you work for Carbon, so let's try for this one to give a non-biased response, please. So what are the different AM technologies that can be used in motorsports applications?
Yeah, so in terms of additive manufacturing as a whole, if you think about things from a materials perspective, there are different additive technologies in the metal space that can bring improved performance or through lighter weight parts or improved design of parts. From a polymeric standpoint, we also have rigid materials that can support a vehicle through brackets or various components, connectors
Erica
throughout the vehicle.
Reconnecting.
Oh, is my connection slow?
No, that's
Can you hear me?
Yes.
Okay, sorry.
Yes, no problem.
And from a carbon perspective, we have rigid components that can also enable intricate designs. We're seeing a lot of success within electric vehicles and the new and the additional brackets that are necessary for all the electrical wiring throughout the vehicle. And also from an elastomeric standpoint, we have an elastomeric polyurethane that creates lattice components that are like premium foam replacement. And so we've used this in some Formula One race cars to provide ventilation within seats, more comfortable seating, having variable stiffness or variable response seats that enable performance drivers to be more comfortable while they're focused on their task at hand. And so from a variety of materials and being able to suit a variety of needs, we've been able to do that. And as I mentioned, with Carbon's technology, we're able to print a lot faster and be able to hit economic targets that are enabling us to be in broader mass market vehicles. So it's a very exciting time to be a part of the company and watching it grow as we expand across various categories and vehicles within the automotive industry.
Yeah, thank you, Erica. from a design perspective now, and now this is a question for Andrew. Is it fair
from the speakers a lot of different?
Yes, sorry. Yeah, no, please go ahead, Andrew.
Please go ahead.
No.
I think my neck.
Do you want to add?
I was just going to say that in terms of the materials,
Mm-hmm.
yeah, the materials that we're using, we compete in a lot of different series. So we have the opportunity to implement the technology in many different areas. Sometimes it's prototyping, so we might do a lot of resin-based printing, stereolithography, for example, in our wind tunnel development. We've been able to implement that on the, for instance, the next gen NASCAR Camaro ZL1. We switched to a fully additive development architecture there. We're able to do well over 1,000 iterations of components, saving over $1 million in wind tunnel time and part production costs.
Yeah.
And then we also, on the production, racing production side of things, we're looking at all different types of materials. We use a lot of polyamides, a lot of nylons, some with fillers for those higher temperature applications, significantly as well. So, high quality materials for stainless steels, high temperature aluminums, Inconels, a lot of different options that we get to work with and then understand and pass down to the mainstream production engineers.
Yeah. Andrew, is it fair to say that DFAM, Design for Additive Manufacturing, enables to have greater control over the race car strength to weight ratio of metal 3D printed parts, especially, and why?
Yeah, absolutely. So one of the benefits of DFAM, the ability to design added complexity with additive with a lot less constraints is the actual ability to use topology optimization. It's not necessarily a new technology, but the part geometry that it output was oftentimes so difficult to make with, say, machining, where you have a lot of organic ligaments. Now those are completely manufacturable. So we do a lot of work with topology optimization or generative design, if you prefer, to only put material where it needs to be to manage for stiffness. And in that way, through the DFAM, we are able to save a significant amount of weight. Example, we have a NASCAR suspension brace, no longer being used at this point, but with the new generation of vehicle. But we were able to take a stainless steel brace, convert it to titanium, and then not only convert it to a less strong material, but reduce the volume about 5%. So the net result was a 46% weight save. We increased stiffness as well. On one side from 8% to another side, we had 46%. So significant opportunity to increase both specific strength and stiffness through DFAM.
Okay, thanks, Andrew. Before we move to the next question, I would like to remind the audience that they can still have time to write their questions in the Q&A chat in front of your screen. Andrew, what about the other AM technologies?
What was that?
What about the other additive manufacturing processes?
The older?
Yes. Can we apply? If we use the DFAM concept as you just explained, are we always going to have, greater control over the race car strength to weight ratio of the parts, of the 3D printed parts?
I'm sorry, I don't quite follow the question. Maybe my audio might have cut out.
Yes, you just respond to questions regarding the DFAM concept and how it can enable to have greater control over the race car strength to weight ratio for metal 3D printed parts. Yes, so I was asking if the same applies to other additive manufacturing technologies.
Yes, absolutely. It's just the same thing. The CAE, the FEA that we use for topology optimization, works just as well with, say, a polymer material. We're able to, increase the strength to weight, or the strength to weight ratio, improve it by doing things like consolidate components. So taking multiple AM parts, making them into one, and that works really well with a polymer material as well as a metal material. So we can do things like, increase or reduce the number of fasteners, reduce the number of potential leakage or breakage points, all while saving weight. So kind of all the best benefits in one. Moreover, increasing the complexity of the geometry if that's going to be something that's beneficial.
Thank you. Erica, in the manufacturing value chain, materials are often mentioned as one of the key items that prevent engineers to achieve high performance, as opposed to improvements at the hardware or software level. Is it the case here?
Well, I certainly believe that there are that materials are critical to the entire value chain, and being able to meet the requirements and specifications of the end part is all based on the material and how it's manufactured. Our material scientists at our team, I have to give so much credit to them all the time for the pace at which they're able to create and scale new materials, and how they're able to open up new markets for us just because of the material and what the material capabilities are, whether that's making stronger materials, materials that can have a improved green strength so that they can print faster, or materials that can be flame retardant or flame resistant. However, I will say that I think the beautiful part of additive manufacturing is it's a space where materials, hardware, and software all come together and play together in order to make a superior product. And across the entire additive manufacturing industry, we're seeing advancements in not only the materials, but also the hardware and the software. In some cases, where additive manufacturing is leveraging materials that we've had for all of time in powder form, we're coming up with new ways to be able to manufacture different parts, and using software to have improved AI or automation or learning to continue to have improved final products and parts that can improve the performance of vehicles overall in motorsports or in automotive in general. So yes, I certainly know that materials is so important, and the advancement of materials are so important, but it also is so necessary to continue to innovate from a hardware and software space, and all three of them is where they play together.
Okay, thank you, Erica. Andrew, this is a little bit, a technical questions. I wrote dynamic improvements are often said to be the best way to enhance performance. How does AM come into play at this level?
Sure. Yeah. So one of the best ways is with the freedom in the wind tunnel to create any geometry and then to create it quickly and run multiple iterations. We do a lot of work in CFD, of course, but it may take 48, 72 hours to complete a CFD run, whereas in 15 minutes in the wind tunnel, we'll know if the part has it or not, and we'll have a slightly higher fidelity in terms of predicted on-track accuracy as a result. So that's nothing new. I think Motorsports has been using wind tunnel or additive and wind tunnels for a long time. They were actually one of the first adopters of it. But I think the widespread nature of it is significantly increasing. And then if you look at the on-vehicle production parts, there's a significant amount of work happening there too. So things like freedom in terms of ducting. Maybe it's beneficial to have a cooling duct that changes for every track you go to or for certain types of tracks. And if a race team or GM is cutting a carbon fiber mold, like we would have probably done in the past, it's going to be a lot harder to cut a new mold to justify, that high amount of iteration. But now with additive, where we can just change the digital file and more or less hit the print button, put it on the car, it gives us a lot of freedom in terms of optimizing the aerodynamics for specific tracks. And then, of course, the freedom that we have in terms of geometry with additive versus some of the other, more conventional technologies is a big enabler from the aerodynamics aerodynamic side as well there.
Okay. Thanks, Andrew. We have one question, and I believe that's for you, from Leonard. Which software do you use for topology optimization and DFM?
Sure. So I don't think I can get into specifics, unfortunately, on that. But we've trialed a number of different softwares, and we found the one that's best for our particular types of applications. So I think it's a little bit of an operational question in terms of what types of parts somebody is designing. Some of those softwares are going to be better for certain types of parts, and then some of those softwares are going to be better integrated into the systems that are used in that organization. We have found that of the ones that we tried, we got good results with all of them. We just had to ask ourselves, what was most important, what was easiest for our designers to use. But yeah, good results with all the ones that we trialed. One of the things that we really had to, I think, be concerned with was how well the visual results were presented, so that the designers, when they got these output shapes, like with stress maps on them, were able to really understand what changes might need to be made to augment the output of the topology designs. We had to look at, who's doing a really good job with replicating those surfaces from the mesh to a solid surface that can actually, then be modified through CAD. Yeah, I'd say, it's not anything surprising. So if you look at the players in the market, it's probably one of those.
I think that you wanted a name. Leonard, I hope that these response answer your question. So Erica, to make improvements in overall performance, and this taking into account weight, force, and inertia, could you mention some of the real-world parts that can be improved using AM in the motorsports industry, obviously?
Yeah, so as I mentioned, we have created a variety of components throughout the vehicle, inside and outside, for our customers. One of them, most notably, we've looked at how to optimize and make common parts, but very intricate parts, by, instead of having maybe left hand or right hand brackets, having a common bracket that could not be made through traditional manufacturing or injection molding because of the topology optimization required in order to meet both needs of left and right hand sides. So that's an area where we've seen parts on vehicles, and we continue to grow in that space, as well as connectors, and being able to, again, have very intricate features in order to have connectors in various parts of electrical components and equipment throughout the vehicle. And finally, we've seen applications around seating, and being able to improve ventilation and comfort and the overall, and even provide a more custom experience, again, really for those elite Formula One racer drivers, in order to have a more comfortable experience in vehicle. But we work with a variety of customers, and I'm interested to hear actually Andrew's perspective on how they've used additive within GM to make specific components, or whatever you're able to share, Andrew.
Sure. Yeah, it's been a lot of fun actually working on those types of projects, because they're going to a human as opposed to a car. So some of the areas where we've been able to make improvements for specific drivers is in cooling. So the entire system that's cooling the vehicle as a whole. One of the series one of the vehicle programs has done a great job of integrating several components all into one. So it's a driver cooler / drinks cooler, and able to save a significant amount of weight there. And then even things, like customizing how that airflow is delivered to the drivers, because they all use different helmets, right? So maybe you have a general concept of your design, but it needs to be slightly modified to work for, Bell or Simpson or whatnot. So that's been one area. We've also seen a pretty good amount of traction in the pit crew side of things. So, you know, even among different teams within an organization, you know, where you maybe have certain crews may want to, you know, optimize a certain area. They might want to focus on a certain area, have, you know, the ability to be organized in a way that they weren't before, or be able to, you know, look at the vehicles when they're coming in ways that that they couldn't do with some of the conventional technologies. So we'll do a lot of customization work in that area. And then I think, yeah, from the vehicle side of things, doing some customization work as well when the vehicles are going track to track, although that's limited depending on, you know, what series you're in and what component you're talking about. Sometimes there's a homologation process that.
Yeah. Thank you. Sorry for the connection issues that we are currently facing during this conversation. We just got one question from the YouTube Live. What are the most important criteria to take into account in the choice of an AM process for a motorsports part? I believe both of you can answer these questions. So, Erica, do you want to go first?
In terms of important criteria, when we're supporting our customers, we really look to them to be the experts in, you know, as I mentioned, what they're targeting and what their end use cases or what the requirements are for their production parts at scale. So from a motorsport specifically component, you know, our customers have been focused on really wanting to improve performance. So that comes from reducing weight of parts, having a topographically optimized part, or being able to make intricate designs and iterate faster in order to be able to test out different parts or designs on components on vehicles in order to see what works and to be able to move quickly, because of course time is of the essence when they're focused on hitting a certain performance and continuing to innovate so that they can continue to be the best performing vehicle in their field.
Thanks, Erica. Andrew, do you want to add something?
Yeah, just the classic engineer answer of it depends. And the way we get around that is we do a lot of design thinking where we go out to the race team shops. We meet with the engineers that are internal working on some of our propulsion systems. We see what they're doing firsthand. We find out what their pain points are, and then we figure out the right additive technology or approach to solve that. You know, what one organization may be wanting to do, it could be completely different from another. So I think, you know, it's key to get out there with a group of people that are highly familiar with the technology to see where those opportunities might be. So when, you know, when an engineer is saying I'm having a problem with this part, it's possible to match the technology to it. Certainly, you know, strength, stiffness, temperature resistance are some of the key things that are constantly required and constantly asked for, that we're always trying to improve.
Yeah.
Yeah, and then Erica mentioned a lot of the other types of things that we look at as well.
Okay, so my colleague just posted another question from the YouTube Live. Those TO, I believe that's topology optimization. Does TO differ from one AM process leverage to another, or does it lead to the same result no matter what AM is utilized?
It can certainly vary. A lot of it's based on the material properties that you're using and the material capabilities. So a part optimized for one manufacturing method or material may look different than a metal part. For example, if you're optimizing in a certain polymeric or plastic part versus a metal part, the optimization of the forces on that part and being able to take a look at the FEA and making sure that it's meeting whatever structural loads are required will change what that end part looks like. And I'm sure Andrew has some real world examples or experiences with that.
Yeah, I was going to say that.
Yeah.
Yeah, I've got a couple. So I think the basic approach when we start off with topology optimization is pretty standard, where we look at what the constraints are, what the applied loads are, what the design space is. That doesn't really change by the technology. But from the time that we get our first possible output, we're looking at what might need to be modified to improve it for printing in the specific technology. Usually we have a technology in mind. We know if it's a metal part, we're probably going to be doing laser powder bed fusion. If it's a duct part, we're probably going to be using some sort of polymer or powder. Not necessarily, but oftentimes the case. So we immediately start looking at what the output is and saying, where is there going to be an overhang? Where is there going to be a support? Where is there going to be trapped powder? And we just iteratively step through that process and add material or change material and features as needed. That's one of the, I think, the most fun areas, of being an engineer in this space, is saying, well, what if we, instead of having to put support structures in between this cavity or this, this open window, what if we were to fill that and then put ISO grids on it, and see what works, what doesn't work, and then take the lessons learned from that and apply it to the next approach. And we've been able to, for instance, going from just a solid surface to one that has, an ISO grid-like texture on the outside, save over 50% weight of the part with a minimal compromise to stiffness. So it's very powerful, implementing some of these freedoms that are available for specific technologies. And one of the things that we like to do, as application engineers is actually be working with the technology hands-on, getting into the machines, using the machines, doing the post-processing, so we understand that at a fundamental level.
Okay, thanks, Andrew. To both of you, do you think regulations in the motorsports industry affect or limit the ability of engineers to deliver innovation or performance? Any examples, to share regarding that, Erica?
I would say that the beauty of additive manufacturing is that engineers are able to unlock new ways of designing and innovating on their parts, and pushing the boundaries of performance. So, of course, naturally, though, there are always going to be regulations for within the automotive and auto sports industry. And those constraints have to be taken into account like any other requirement when an engineering is designing a certain component or vehicle. But I would say that, in my experience early on in engineering, the creativity that comes out in the ability to really maintain the safety required and a strong focus on creating a part that performs well while being able to still be a safe component is such a critical part of the industry. And of course, so anyone could say that any constraints may limit some form of thinking, but those regulations are there for a reason, and I'm constantly impressed with how engineers are able to find creative ways to continue to innovate and make improved parts.
Thanks, Erica. Andrew?
Yeah, absolutely. I think it's, as additive technology grows in popularity, it's something that the regulatory bodies need to address, because a lot of the different teams are using this technology. So number of the regulations that are put in place, not just for additive, but just in general, are to promote the sustainability, the long-term, likelihood that the sport is going to prosper, that the teams who are involved are going to be able to keep participating in the future and remain competitive with one another. So, that's where things like budget caps come in. And when it comes to additive manufacturing, I think there are definitely two ways to approach this, and I see some of the regulatory bodies doing so. One is there are some components that are going to significantly add to an increase in cost, You know, for example, a reciprocating or rotating component inside an engine is going to be very expensive to develop from an additive manufacturing standpoint. You're probably going to need to do significant amounts of fatigue testing. You're going to need to, you know, destroy a few $20,000 prototype race engines, maybe more than $20,000. You're going to have to be doing CAT scans on CT scans on failed parts, etc. Right? So that could very quickly spiral out of control. But on the other side, there are a number of components that are significantly cheaper to make with additive manufacturing. You know, things where you can get away from using carbon fiber, you can get away from having to cut a tool for casting, because now you can direct metal print the part. So I think I see most regulatory bodies being aware of that difference, and I think it's something good to continue to be aware of as we move forward. Just because it's a new technology doesn't mean it's going to be you know, a more expensive technology. And you know, oftentimes one of the benefits of additive is that you can make it, you know, better, however you want to define that. You can make it faster and you can make it cheaper. So it tends to be a win in a number of scenarios.
Yeah. You were talking about, you know, regulations in terms of sustainability, and I wanted to ask if there is any progress that motor racing is making in the area of low carbon, because I believe that's a very, very big challenge in this field of activity, right?
Yes, it's certainly there's a lot of interest, I think, from everybody involved. You know, as GM and other companies try to move towards a zero emissions future, what are we doing to make sure our racing strategies align with the corporate strategies? And you know, I guess cheekily, I would say, with additive manufacturing, we're saving weight, so we're increasing fuel economy, we're getting better aerodynamics. You know, so we're getting higher lift to drag race ratios. So that's, you know, maybe how directly we're helping.
That's too easy. That's too easy as a response, Andrew. Okay. Yeah, I'm gonna say, Erica, do you have a better response to this?
Oh, certainly not better, but a different. But I do agree with what Andrew was saying. But from carbon's perspective, from a materials perspective, we're always looking and focused on sustainability and understanding how to improve the manufacturing of our materials. Yeah. We're moving towards making materials that are more plant-based, and ensuring that we have a more sustainable manufacturing and supply chain, and the ability to improve the parts that we're providing to our end customers. So from our perspective, primary focus is around making more plant-based materials, as well as improving, you know, again, to iterate what Andrew's saying, improving the components that can enable to, you know, better fuel economy, less fuel consumption. Overall, I think that's going to be another path where we can partner with OEMs, especially within the automotive space, in order to reduce our carbon footprint.
Okay, thank you. Thank you. Andrew, do you have any questions for Erica, because you are reaching the end of the panel?
I guess when you look at some of the work that you've done in motorsports with the carbon technology, what have you been most proud of? Where do you think some of the biggest successes are? Are they the seats in Formula One, or are there other areas that you point to as well?
Yeah, well, this is an area where we're certainly growing. I would say overall, I am so proud of our customers and their ability to design for DLS and use our full platform of tools in order to improve the parts and improve the parts that they're making and improve their vehicles. I get so excited when we hear about the next component that we have on production of vehicles. We have a big focus on making parts at production scale, and not many additive technologies are able to do that and to be able to scale to the levels that we've seen at Carbon. So very proud of the focus on production vehicles and end use parts, to move beyond prototyping and really focus on production within the automotive industry.
Yeah. Erica, do you have any questions for Andrew?
I do. And I think we've touched on this quite a bit throughout the presentation, but Andrew, you mentioned earlier very specifically that, you know, General Motors, GM really wants to focus on quickly releasing vehicles and improving time to market and iterating. So from like a time to market or speed perspective, or being able to create the next innovative vehicle at a faster pace or through more iterations, and so being able to iterate more because you're able to move more quickly in the same amount of time, or do more iterations in the same amount of time. What are some examples of leveraging additive in order to meet that improved pace?
Sure,
question,
we have.
Erica.
Oh yeah, very good question. Thank you for that. So we have some examples where, due to the supply chain shortages that we've all been experiencing lately, we've actually been able to produce additive manufactured parts for the vehicles to get them out of the plant. You know, maybe there's a an adapter, there's a panel, there's something that would normally be made with an injection molded component, and we've actually been able to prove that the additive component is completely suitable for that application, and that allows us to get vehicles to the customer quicker ultimately. And maybe it's something where we can't make 1 million of them a year and have it make financial sense, but if we're only making enough to meet the immediate needs, we certainly can do that. And then, I think we'll see some things here in the near future, and some of the ideas are present in the concept vehicles that we've released, where the vehicles are being better tailored toward the individual customers, the individual users, so that their experience is as good as possible, and having things like more options that they can choose from when they're asking for delivery of the vehicle is something that additive could help create.
Okay. Andrew, I have one question before you give your concluding thoughts, and the audience, if you have any other questions to share, please, that you still have a few minutes to ask any questions to Erica or Andrew before we close the panel. And that's a tricky question, that's a tough question, but I believe it requires a really a honest response. So you have been, adopting AM for several years now. By you, I mean GM. And if you had to share any improvements that manufacturers, should do to advance AM technologies and other, related processes, in this industry, what would you say? Well, what improvements do you expect from AM technologies providers?
Sure. I think the good news is the AM providers like Carbon and the others out there have been very receptive to automotive's needs and differences. The volumes that automotive creates are very seldom reached in any other industry. Certainly, any that have the type of demands that automotive has on it. So they've been very receptive, and some of the things that we've been asking for and they've been helping with, are improving the machine time, the time that it takes to print the part. When we look at our cost models, that's still the most expensive component of the additive overall cost. How much time did it spend in the machine? And some of the ways that that's been improved upon is moving from a serial fusion process, however you want to define fusion, to a parallel fusion process. So instead of having, for example, one laser beam, maybe you have an array of laser beams, or maybe the entire bed is covered with a fusing energy source. So that's one of the big enablers that's really going to be able to 10x the part production speed. And then the other side of it is the post-production time. So doing things like being able to print without supports, having the supports be completely soluble, and then increasing some of the automation in those areas. If it's a powder-based process, right? How do we get that powder off consistently, quickly? If we're trying to do this at mass scale, the ability to utilize the same type of infrastructure of automation that we use for any other technology needs to be applicable and applied to additive.
Right. Thank you, Andrew. Any concluding thoughts for this panel? Erica, do you have any last thoughts that you would like to share regarding, the use of AM in the motorsports industry?
Yeah, overall, we've talked about some of the advancements in the technology, and I'm so excited and honored to be a part of this panel. Really looking forward to seeing how we advance, and Andrew, even from like a carbon GM perspective, what we can do together to improve, automotive parts on vehicles, or from a motorsports perspective at scale. So, overall, really thrilled of where the industry is going, the advancements that we've done, the innovation that engineers continue to drive. And thank you again for asking me to be a part of this panel, Kitty.
It's a pleasure, Erica. What about you, Andrew?
Yeah, very happy.
Any last thoughts that you would like to share?
Yeah.
No, I was just asking the same question.
Yeah. I mean, the fact that we're, even here having this conversation, talking about how motorsports relates to production, I think is great, and something that is showing there's a clear tie-in and clear benefits. If we look at, some of the technology transfer, I've worked in a lot of different aspects related to motorsports, and additive has the most direct technology transfer from motorsports into mainstream production, materials, processes, digital software, etc. So, I think there's a really good case for continuing along this path, and having the additive engineers integrated into the mainstream groups is the way that technology and that wisdom is going to get dispersed across, a wider footprint and make an even bigger impact. So having these types of discussions, I think, is going to be key to that. And figuring out, because all of our technology roadmaps in motorsports additive go from motorsports R&D to motorsports production to mainstream production. They waterfall into that in that order. So continuing to progress motorsports so that the mainstream technology is able to implement that capability in the future is something that's going to be key, and something very exciting to be a part of.
Thank you, Andrew. Well, from an editor standpoint, I can only say that I look forward to see how OEMs and machine manufacturer, AM technologies provider, can work together to advance this specific field of activities. And on these good notes, I would like to thank the audience for joining us for this virtual panel dedicated to the use of AM in the motorsports industry. I hope the panel has been useful to you. I hope you have learned very great insights from Eric and Andrew present here. Sorry again for the connection issues that we faced during the conversation. And I would like you to stay tuned for the next panel next month that will welcome speakers from NASA, Authentize, and Silicon around a topic dedicated to data in additive manufacturing. Thank you again, Eric and Andrew, for joining us, and stay tuned wherever you are in the world. Thanks.
Thank you, guys.
Thank you both.
Thanks. Bye.
Bye.
Have a nice evening.
Thank you.